Rogerio Rosenfeld, which, by the way, is also one of the organizers. So he kindly offered to also give lectures about cosmology. So let me give you a short introduction of Rogerio. So Rogerio did his PhD at the University of Chicago. After that, he did a postdoc at UCLA, University of California in Los Angeles. After that, in the Northeastern University, and then at the University of Sao Paulo. And he's currently professor at IFT-UNESP, and he is vice director of ICTP-SAIFR. So please welcome Rogerio Rosenfeld. Rogerio, please.
Okay, thank you very much. So you can hear me, you can see my screen, everything is set?
Yeah, everything works fine.
All right. So I was not supposed to teach in this school because I'm one of the organizers, but I volunteered, and maybe you will regret that, hope not. So my background is in particle physics. I did my PhD in phenomenology of the Higgs factor, etc.
Rogerio Rosenfeld, which, by the way, is also one of the organizers.
I started to work in cosmology, like 10, 15 years. And so I was doing some mostly theoretical work in cosmology. And then in the last 10 years or so, I went even further in cosmology and joined some experiments in cosmology. I became a member of two experiments. One is the Dark Energy Survey, and the other is the LSST, the Legacy Survey of Space and Time, and probably I'll talk about them in this set of lectures. So the way I decided to organize this set of lectures is in three parts. And part one, I will describe how the universe looks on average. How do we characterize the expansion of the universe, acceleration, thermodynamics, distances, etc. Part two, I talk about origins, so origins of atoms, for instance, origin of baryons, origin of dark matter, origins of small inhomogeneities in the universe. And part three, I would describe what I would call the perturbed universe. So not the average, but perturbations in the we know we live in perturbations in the universe. So we have to understand how perturbations evolve and how can we measure the universe today and get information about the basic cosmological model. So this is more or less the plan of this talk. You can probably see my mouse. I'm professor at IFT-UNESP and ICTP-SAIFR. You probably don't know much about LINEA, so I just talk a little bit about this laboratory, which actually gives support to many experiments in cosmology. And this is the LSST, and this is the Dark Energy Survey. There's other like ESI, the Dark Energy Spectroscoping Instrument, that's starting data this year. Anyway, so just some references that people can look up if they're interested. There are some lectures that I recommend, especially Bauman's lectures. If you want to have some very nice introductions to cosmology, I do recommend this set of lectures by Daniel Bauman. They're here. There are lectures by Jim Klein and lectures by Bauer and Plen. And then there are classical books on cosmology. Classic, really classic, Steven Weinberg's 1973 book, Gravitational Cosmology. So it's 1973, it's a bit outdated, lots of general relativity and tests, etc. He has a more recent book called Cosmology of 2008. And I learned most of my cosmology from this book by Rocky Kolb and Mike Turner called The Early Universe. So this is a book of 1994, and I still find it really good. It's outdated, but it's a fantastic book, and it has especially on one appendix that's very, very useful with constants in all different units that I use all the time. And there's also a classical book by Jim Peebles, Principles of Physical Cosmology. And then there's a second edition of a book by Scott Donaldson, and now there's a new author. So it's Scott Donaldson and Fabian Schmidt, and Modern Cosmology. This is a very recent book. So these are all books I recommend for people that want to study. So the plan of this first set of lectures of the average universe is I want to spend some time about, this is a course of cosmology. So it's a basic cosmology course for particle physics. So I want to motivate, and so with an introduction, cosmology, and this is what I will do first. Then I will do a brief review, very brief review of general relativity. Then I'll talk about dynamics of the universe, and then finally the thermal history of the universe. So I'm not sure how far I will go, but it's first lecture. But so if there's one message you should take home, it's a message from this series that you probably heard about. So our whole universe was in a hot, dense state nearly 14 billion years ago when expansion started. Okay, so in this introduction, I want to say, why should a particle physicist learn cosmology? So I want to motivate you to learn a little bit of cosmology. And I want to start by saying that some of the main evidences for physics beyond the standard model comes from cosmology. So we know that there should be something like 25% of the universe is being made of something called dark matter. 70% is made of something like dark energy. We know there must be a phase of inflation. All these things are related to physics beyond the standard model. I see that there are many messages on chat, but I cannot read them. So Enrico, stop me if there's something important.
Yeah, okay? No, don't worry. There are no questions for the moment.
Okay. So I want to stress that particle physics affect cosmology. For instance, the origin of matter and antimatter symmetry, why there's more matter than antimatter. This has to do, of course, with particle physics. What is the cause of inflation? There are some models where even the Higgs boson is causing the inflation. Not a very natural model, but there are models like that. Neutrinos, standard model particles, they're very important for the formation of structures in the universe. And also, there could be phase transitions in the universe. Andrea talked about spontaneous symmetry breaking and granified theories. So granified theories, they go through symmetry breaking in the early phases of the universe. Depending on the nature of the phase transitions, many signals can arise, gravitational waves, etc. Now, cosmology also affects particle physics. For instance, the evolution of the universe may be responsible for electron symmetry breaks. So there are models out there where the fact that the universe is expanding, things are changing, can explain phenomena in particle physics. For instance, electroweak symmetry breaking. This goes under the name of relaxium. Maybe you hear some more about this next week. So the early universe can also be seen as a test bed for the standard model or beyond the standard model physics. As we know that the standard model vacuum is not stable, it's actually metastable. So that can have consequences in cosmology. New physics can be tested in the cosmic microwave background. Inflation is also a test bed for new models. Matter-antimatter symmetry I already mentioned. Primordial non-Gaussianity. So we'll see a little bit that we can describe these perturbations in the universe as some Gaussian random field, and that's a prediction from inflation, from simple models of inflation. And non-Gaussianity can, if there is some departure from this Gaussianity, that can imply some different types of primordial gravitational waves are believed to be generated during the inflationary phase of the universe. Stochastic gravitational waves from phase transitions, granified theories, for instance, can also be produced and may be detectable. There's something that became popular in the last 3-4 years, this thing called cosmological collider physics, where you can test the effect of very high energy interactions in producing, for instance, non-Gaussianity. And you can test modified gravity also. So models that are beyond general relativity. And gravity and geometry may play an important role in particle physics. I just want to tell you that when I started as a phenomenologist, I couldn't care less about gravity. The reason being that when you test things in accelerators, gravity is completely negligible. You're colliding protons, electrons, etc. So gravity plays no role when you talk about particle physics accelerators. However, this has changed in the past, I don't know, 20, 25 years. And especially because now there are models which have more than usual 3+1 dimensions. And these models with warped extra dimensions or inverse extra dimensions has different geometry, and that has consequences for particle physics. Can predict, this type of models predicts new particles from geometry, called Kaluza-Klein excitations, radions, etc. So this can probably be seen also next week. And models with extra dimensions can also change the evolution of the universe, and hence they can be tested as well. So this is just a motivation for you guys to learn a little bit about cosmology. Cosmology is really a field where you can test different models in particle physics, and nowadays we have more and more precise observations to test these models, and I want to talk about these observations toward the end of this course. Now, you already know and heard from Andrea that the standard model of particle physics, it worked really well, but we're not really happy with the standard model. So the origin of neutrino masses is not contained in the standard model. Dark matter is not contained in the standard model. There's something called the hierarchy problem. Why did Andrea rapidly mentioned is that why the electroweak symmetry breaking scale is so much different from Planck scale. So there are motivations to go beyond the standard model in particle physics. Now in cosmology, we have situation that is more or less similar. So we have a standard model of cosmology, which we call lambda CDM. So it's a model of the universe which has a cosmological constant, which today is responsible for approximately 70% of the energy density of the universe, and cold dark matter, meaning non-relativistic dark matter, which is responsible for 25% of the energy density of the universe. And this standard model of cosmology, which is really based on 6 parameters, it explains all the observations we have so far. So we have lots and lots. I will talk about some of the observations, and all the observations can be explained in the context of the standard model of cosmology, lambda CDM. But we're not happy with the lambda CDM. For instance, we don't know how to naturally explain the value of this cosmological constant. So there are models that try to go beyond this lambda CDM. And models either beyond the standard model or beyond the lambda CDM model, there are many of these models that have been proposed by theorists, and it's our job to see what nature has chosen. So, it's not a matter of proposing the theories, but we have to check and see which ones are actually chosen by nature, which one describes nature. So cosmology has recently become a data-driven science. So we entered in the last, I would say, 20 years again, an era of precision cosmology. So at the risk of giving out my age, when I started to work on cosmology, the age of the universe was given as with an uncertainty in the exponent here. So the age of the universe, when I started studying cosmology, given as 10 to the 9 plus or minus 1 years. So it could be 10 billion years, it could be 0.1 billion years. It was very, very uncertain. And now we know the age of the universe with a very high precision. And this was a game changer in cosmology. Now cosmology really became a precision science. So there are many experiments out there that are taking a huge amount of data, and this data are being analyzed in order to find out which model best describes the universe. And I want to also emphasize that cosmology became a respectable science, due in great part to one person, Jim Peebles. I already mentioned Jim Peebles, one of the books, the classical books in cosmology. Has like 3 books in cosmology that really taught a generation, and he put cosmology in a very solid physical basis. And I think it was very well deserved that he shared half of the Nobel Prize in Physics of last year. And if you look here, is for his it's for theoretical discoveries in physical cosmology. So he's a major name, a major person in bringing cosmology to standards that are same standards in particle physics. And that was an incredible work that took decades to consolidate. So he won, I think he won the Nobel Prize for his incredible work during many, many years. So yeah, we'll talk a little bit more about that later. So this is more or less the, this is the poster of the history of the universe. We believe that there was something we call inflation here at very, very early stages of the universe. And then the universe was dominated by radiation. And then at some point, radiation decoupled from matter. We'll go through this history later on. And structures start to form. So the small fluctuations were formed here. Sorry, during inflation, they evolve. And they're seen in the cosmic microwave background. And here, there are dark ages where no objects are formed, and stars start to form, galaxies start to form. And we believe we entered a phase of accelerated expansion again in the recent history of the universe, called, which is dominated by dark energy. So it's accelerated expansion. I'm going to talk about also later. So I mentioned that there are several cosmological probes, cosmological observations that one can make in order to test different cosmological models. And these are just a few of these cosmological probes. So the cosmic microwave background has CMB, which is the, if you want, is the leftover radiation from the Big Bang. It's an amazing, pristine observable that carries a lot of information about the universe. And the observation of the cosmic microwave background has gone through different stages, and with the Planck satellite, which stopped taking data in 2015 or 16, it reached a whole new level. Much information comes from studies of the cosmic microwave background. Big Bang nucleosynthesis, which is something we're going to see also in these lectures, and the formation of light nuclei in the universe in the early few minutes of the universe, 3 minutes, also is one of the pillars of cosmology. Talk a little bit more about that later. Supernova type 1a, specifically type 1a, so supernova are exploding stars, and the type 1a supernovas can be made into standard candles, and that can help to trace out the history of the expansion of the universe. And that's how it was found in 1998 that the universe was not only expanding, but it was expanding in an accelerated way. So it was a big surprise. Supernova of type 1a is one of the important observables. There's something called baryon acoustic oscillations, which has to do also with the formation of galaxies. This is something I'll talk later. Effects of gravitational lensing. So galaxies, the shape of galaxies can be, or shape of any object can change if the light passes through some matter that has some potential. Gravity potential can distort the objects. Goes from strong lensing, where you can actually see multiple images, to weak lensing, where you only see small distortions of the shapes of objects. And this has become very important in order to, again, map out the distribution of matter, not only baryons, but the whole matter in the universe. And also the number count of clusters of galaxies. So galaxies, they usually are inside larger structures called clusters of galaxies. And if you count the number of clusters of galaxies in the universe, a function of the mass of these clusters, this is also a probe of cosmology. So these are all probes that cosmologists are using in order to derive limits about models that describe the universe. And this is just one slide with different pictures of probes. So this is the cosmic microwave background. This is the Big Bang nucleosynthesis, supernova. This is the tracing of dark matter, weak gravitational lensing. This is the just distribution of galaxies in the universe. And this is the effect of baryon acoustic oscillations. Anyways, we're going to go through some of these observables later on. So in this 10, 20 years that we have seen this rapid development in observational cosmology, a consensus has emerged. So this is the standard cosmological model. And this consensus cosmology, or concordance cosmology, some people, rests upon these three pillars, which we're going to discuss: dark matter, dark energy, inflation, and they all imply new physics. So this is a spoiler of the end of the course. You probably already had seen this figure before. So we know that we don't know what 95% of the universe is made of. So there's this pi here, and 5%, basically 5%, 4.6%, roughly 5% is atoms. So things that we are made of. And the rest is something we really don't understand. So roughly 70% dark energy and 25% dark matter. Neutrinos are negligible, light today is negligible, and we are going to see the effects of neutrinos and radiation later on. So we don't know what dark matter is, and there are several models. The simplest one is the so-called cold dark matter. Hot dark matter, so dark matter particles that are relativistic, have been ruled out by structure formation. We will touch that later. It could be cold, it could be warm, it could be fuzzy, like very light particles that have Compton wavelengths of the size of galaxies. And we don't know much about the interaction of dark matter. We know that it doesn't interact with normal matter significantly, but it can self-interact, and that can change the behavior of dark matter. And we know even less about dark energy. It can be a new degree of freedom, modify gravity, quintessence, Galileans, F of R theories from Desky, beyond Mondersky, massive gravity. We don't know if it interacts with matter. We don't know if dark energy clusters, etc., etc. So there are many, many things we don't know, and we would like to find out about these things. So now I will start. Sorry, this is a good time to stop. This was just a motivation kind of talk. And do you have any questions or curiosities at this point? I didn't do anything, but just mention a bunch of things. Are there any questions, Enrico?
Yeah, if there no, for the moment, no.
Okay.
So is there somebody with some urgent question? So Bernardita is asking, are you going to talk about FRB?
About what?
FRB, I'm sorry. What is FRB?
FRB? I have no idea what FRB is. So probably I'm not going to talk about FRB.
Okay. Fast radial burst. Okay. Are you going to talk about? No.
This is too astrophysical for me.
Okay. No. So sorry, Bernardita. No, not in these lectures.
Sorry.
Something else? How do you get the percentage of components of the universe?
That's the subject of the whole lecture. So
okay, so Christian, hold on a bit. That Rogerio will answer your question along these 5 lectures.
Yes. Okay. Maybe I should continue, right, Enrico?
Okay. Yes, I think you can go on, and then later on I will stop you if there are many other questions.
Okay. Good.
Okay.
So first, I want to give you a brief review of general relativity. And general relativity, of course, is the force that rules the universe at large scales. So forget about all the other forces. Forget about weak forces, strong forces, because they're short-ranged. And you should also forget about electromagnetic forces, because the universe is overall neutral, charge neutral. So what really describes the universe, what really rules the laws that controls the motion of the universe as a whole is general relativity, it's gravity. And fortunately, we don't have to go into discussions about quantum gravity, because classical description is sufficient in most of the cases we're going to talk about. We're going to talk about, what happens at late times when galaxies form, etc. That's mostly what we're going to be interested in. So just to start, really, we can do classical field theory, and classical field theory in a nutshell can be described by fields. So you find out what are the fundamental degrees of freedom that you want to describe by your theory. I just want to recall that they're not always physical. Maybe you already know that sometimes when you describe a photon, you have 4 degrees of freedom, but you know that 2 of these degrees of freedom are not physical. So maybe Andrea will talk about this. And then you have this, in order to know how these fields interact, you write down a Lagrangian to describe its dynamics, and then the usual Lagrangians based on, you have as a guide to build Lagrangians on symmetries of nature, or Tinker symmetries of nature. And then from the Lagrangian, you build an action, and from the action, the equations of motion, which are stationary points of variations of the. So Einstein's equation, which is this one here, so this is something we call the Einstein tensor, and this is the Riemann tensor, the Ricci tensor, and the Ricci scalar here, and G mu is the metric. So the Einstein tensor is composed of these 2 parts here, and Einstein equation is just saying that this part here, which actually I'll show you later, but is related to geometry. So basically, if you give me the metric, I can construct the left-hand part here, the Einstein tensor, and the right-hand side is related to the content of matter and pressure of the universe. So this is the energy momentum tensor, Q mu nu. And G is the gravitational constant. So these are 10 nonlinear differential equations. Tensors are symmetric, so mu goes from 0 to 3, and this tensor is symmetric. And these are nonlinear equations for the metric. So in general, these equations must be solved numerically. So if you want, for instance, to solve in situations like, binary black holes that coalesce and then they fuse and produce gravitational waves, in the last parts of this process, you cannot use any perturbation theory. So you have to rely on solving this very complicated set of equations numerically. Fortunately for us, we'll usually be working in a regime where perturbation theory is valid. And also, there's some other simplifications that we're going to see most of the time. So the fundamental field of gravity is the metric. So this is the metric tensor here, which describes how distances are built from the coordinates of the system. And here I'm going to use this signature of 1 minus 1 minus 1 minus 1. So these are the properties of this metric. In flat space-time, this is Minkowski. So p mu, which is p squared, is c squared minus p squared. So just a set notation, because some people use a different notation, minus plus plus plus. So just to let you know which notation I'm going to use. And this is a slide I stole from Rocky Kolb. If you remember, that's one of the authors of the book that I like a lot, Cosmology. So this is a slide. Rocky Kolb is for those who know Rocky, he's a joker, so he likes to make lots of jokes. And this is supposed to be Moses carrying the table of laws. So there are 10. Remember that the Einstein's equation are 10 nonlinear differential equations, 10 commandments here. So Moses carrying the 10 commandments. And just to remind you that the left-hand side of Einstein's equation is geometry, and right-hand side is matter, energy, and pressure. And as John Wheeler used to say, the left-hand side, you can summarize as space tells matter how to move, because this that's the geometry, and the right-hand side is matter tells space how to curve. So, Wheeler's explanation of GR. So in a little bit more of detail of Einstein's equation. So G, as I said before, is Newton constant, which in terms of the Planck mass can be written as this. Well, so we're using natural units most of the time, where h bar equals 1. So in those units, the Newton's gravitational constant is the inverse of the Planck mass square. The Planck mass is roughly 10 to the 19 GeV. And here, just a word of caution for people that want to learn cosmology. Sometimes people use the reduced Planck mass instead of the Planck mass. This has a factor of square root of 8 pi. So it's roughly 10 to 18. And you see why people use that sometimes, because of Friedmann's equation. Now, so more details about Einstein's equation. So there's something called Christoffel symbols, or sometimes people call it metric connection, affine connection. And this is something, a geometrical quantity that enters in the definitions of the tensors we're going to talk about. And it's one thing is important to know is that it's related to the first derivative of the metric. And the Ricci tensor is constructed from the Christoffel symbols like that. And as you can see, it's the second derivative of the metric, right? Derivative of the first derivative, and here's the product of two derivatives. And finally, the Ricci scalar is just a contraction of the Ricci tensor with the metric mu. So we have all the ingredients that we need in order to write Einstein's equation in terms of the metric. Now, Einstein's equation also follows from an action principle. So this is something I mentioned here. That equations of motion, so Einstein's equation is an equation of motion. There are equations of motion that can be obtained by varying a action and finding stationary points of this variation. And this action, this is beautiful because this is fantastic. This is really a simple thing. The so-called Einstein-Hilbert action it's given very simply as this expression here is integral. So there's a 1 over basically g integral of d for x, the square root of minus determinant of the metric g times the Ricci scalar r, which depends on the metric. And it's called the Einstein-Hilbert action. Maybe you know the history. If you don't know the history, you should read these papers, because in the end, when Einstein was about to finish his paper on his final paper in general relativity in 1915, and he was actually competing with a mathematician, Hilbert, in Göttingen. Einstein went there to do some lectures. Hilbert was expert in getting equations of motion varying the action. And so there is a incredible history about this, who got this action first. It's called the Einstein-Hilbert action. And these actions invariant and their general coordinate transformations. And as I said, G here, small g is just the determinant of the metric. So by varying this action with respect to the metric, you get Einstein's equation. It's amazing. So again, some dimensional analysis. So we're using h bar equals 1. So the metric is dimensionless, which means that the Ricci scalar, remember, it's the second derivative. The Ricci scalar has two derivatives. So it goes like energy squared. And d for x, of course, is energy to the -4. The action is dimensionless when h bar equals 1. So this Newton's constant that goes here, you just do the math, it has to have dimensions of inverse energy squared. And hence this relation between Newton's constant with the inverse of Planck mass. And as you recall from Andrea's lectures and some questions, we have a coupling that has a dimensionful, it's not dimensionless, it's dimensionful, the theory is non-normalizable. So actually gravity is non-normalizable. And Einstein's equation in vacuum, so when there's no matter, is simply obtained from this variation of Einstein-Hilbert action with respect to the metric, finding stationary points of this variation. That's one way of deriving Einstein's equation. By the way, it was not historically what Einstein did, but it doesn't matter. So let me talk a little bit about the cosmological constant. So 2 years after Einstein wrote his article paper on general relativity, so in 1917, 2 years after that, almost 100 years ago, Einstein decided to use general relativity, his theory, to describe the whole universe, so cosmology with general relativity. And he wrote this paper called Cosmological Considerations in the General Theory of Relativity. In that paper, he introduces the cosmological constant in theory, which does not violate any of the symmetries. So theory continues invariant under general coordinate transformations, just a new constant of nature. And he did that because he thought at that time, and everybody thought at that time, so we're talking about 1917, that if you discount, proper motions of objects in the sky due to, say, rotations of the Earth, etc., things do not move. So universe is static. That was the common belief during that time, 1917. But of course, gravity is only is attractive force. So in order to have a static universe, he needed a force that counterbalanced the gravitational attraction. And so he introduced this anti-gravity effect through the cosmological constant. So it was introduced to stabilize the universe. Of course, this didn't solve the problem because the universe is not stable. I mean, if you perturb a little bit the universe, it will either expand forever or recollapse. Einstein didn't know that either. He postulated a new constant of nature, which we call the cosmological constant. And with the discovery of the expansion of the universe, which was done by Hubble in 1929, this was the beginning of the data saying that the universe was not static. Of course, this was confirmed much more data. The cosmological constant was no longer needed. Einstein called this introduction of the cosmological constant his biggest blunder. So you probably have seen this quoted several times, and you may wonder what is the origin of this quote. And as far as I know, the origin of this quote is by before that. This is the original paper of February 1917, where he introduces. This was not capital lambda at that time; it was just a small lambda, and it was a universal constant describing his equation. Now, as far as I know, the source of this quote by Einstein is a physicist called George Gamow, which I will talk more about him because he was very important in the early development of cosmology. So George Gamow, he wrote several books, including many books on just the outreach of science at the 50s, late 40s, early 50s. His books were amazing. And the reason I went to study physics is because I read those books when I was in high school and decided that I wanted to do physics with those fantastic books of George Gamow. 1 to 3 Infinity, The History of the Universe. There are so many fantastic books. Anyways, George Gamow, he wrote his autobiography. Unfortunately, he died before finishing his autobiography, but it was published anyways, and what was written. And his autobiography is called My World Line, which is a nice name for autobiography. And in this autobiography, that's where you can read, is that much later, when I was discussing cosmological problems with Einstein, he remarked that the introduction of the cosmological term was the biggest blunder he ever made in his life. So this is the source of this quote by Einstein, but people usually, George Gamow was also a joker, so sometimes people believe this. But something that he said is true. So this book was written in the 50s. It says, was Einstein considered the biggest blunder? But Gamow goes on to write that this blunder rejected by Einstein is still sometimes used by cosmologists even today, and the cosmological constant, denoted by the Greek letter capital lambda, rears its ugly head again and again and again. He was right. So cosmological constant was always invoked when there was a problem with the age of the universe, etc. And now with the discovery of the accelerated expansion of the universe in 1998, it's the simplest explanation of the simplest model to describe the accelerated expansion of the universe. The ugly head of the cosmological constant is very much with us. So just one slide about, or two slides about modified gravity. So you can think that maybe, you know, the accelerated expansion is not really a cosmological constant. You may think of something different, that maybe gravity has to be modified in a more radical way. And there are theories called F of R theories, where you generalize the Einstein-Hilbert action by some polynomial F of R. So F of R can be like constant, which would be just a cosmological constant, proportional to the Ricci scalar, this GR, or high order derivatives, and even some people think of having 1 over R, 1 over R squared, etc. And this is our theories that people consider sometimes. Actually, the theory here with R squared was used for, was one of the, I think it was the first theory for inflation. Robinsky inflation was with an R squared term here in the Einstein-Hilbert action. Now, there are many issues with modified gravity. Introduces new light degrees of freedom, new forces, and there are stringent constraints that comes from experiments. And so one has to invoke some mechanisms to avoid the modifications of gravity at small distances, like screening mechanisms called chameleon, symmetron, Einstein mechanism. So this is just to let you know that if you mess with GR, you open a can of worms. They also can have classical instabilities because they have higher derivatives in the equation of motion. This is already known from classical mechanics called Ostogradsky instabilities. They may have quantum instabilities, so the theory may not be well defined. Quantum mechanics, ghosts. And usually they may be brought in the form of GR with some suitable change of coordinates. So people usually say going from a Jordan frame to an Einstein frame, and that will introduce non-standard couples in the matter sector. And then you may ask, okay, so how do I search for modified gravity in experiments, in observations? And my take on that is most people use some simple parametrizations to have models that goes beyond modified gravity, and I talk about that a little bit later. And I like this plot. This is what happens when you want to go beyond general relativity. So this is a plot that I took from a paper of Esquiaga and Zumalacárregui. And this paper, they classify different ways to go beyond general relativity. So general relativity is this black blob here, which is a unique theory of massless gravitons. And you can go with additional fields, and the additional fields can be a scalar field, can be a vector field, can be a tensor field. You can add a mass to the graviton, and you can break some of the assumptions of general relativity, like Lorentz violation, have some extra dimensions, etc. And some of these extensions are being now very much restricted, constrained by gravitational waves. That's amazing. And I talk about just given one very, very simple example now. So some modified gravity theories, they predict that the difference between the speed of propagation of gravitational waves, which I denote here by c sub g, with the usual speed of light c, can be of order 1. These deviations here, percentile deviations, can be of order 1. Now, something very important happened in 2017. In 2017, LIGO detected for the first time, I think it's the only, I'm not sure if it's still the only merger of 2 neutron stars at very, very close distances compared to cosmology. You know, in cosmological terms, 130 million light years from Earth is not very far away at all. And so it was a very bright event, and they could observe easily in LIGO. And why is this important? Is that as opposed to black hole mergers, which they have many, when two neutron stars merge, they can emit light. And this light can be detected. And in fact, the light from this event, which happened in 17th of August of 2017, was also detected by different experiments. So just to give an example, this is my favorite experiment, the dark energy camera. So there was actually a Brazilian involved in the search for this event, Marcelo Soares Santos. And here, the dark energy camera actually observed the event here. So this is 0.5 to 1.5 days post-merger of the neutron stars. After 14 days, it was gone. And this was also observed in different telescopes, different wavelengths, gamma rays, for instance. So, it was also seen in gamma rays by two different experiments, one called Fermi satellites. One was the Fermi satellite, and the other was something called the integral satellite. And they were observed with less than 2 seconds difference from the LIGO observation. So you can see here in this plot, this peaks here, this green line is supposed to be the event in gamma rays. And this line here is supposed to be the event in gravitational waves, okay? So you can see that there's less than 2 seconds difference between these two events. And this is the exercise 0 I wanted to do. I want to take this data that the time delay between the light signal and the gravitational signal was less than 2 seconds, and that the distance of this object is around 130 million light years, derive a bound on the different speeds of propagation, gravitational waves, and the speed of propagation of light. Okay, so this is a exercise that I let you guys do. So it's a good time to stop to see if there are any questions.
So, any urgent question for Rogerio? I think you're going well, Rogerio. Really clear.
Okay. That's that Francesca Acanfora raised her hand.
I don't see. Okay. Francesca, please go ahead.
Thank you. Yes, in slide 26, you named some ghosts. And I'm just curious if they are somehow related to the ghosts that we know in the standard model.
So the ghosts we know in the standard model are the so-called Fadeev-Popov ghosts. Probably is that what you're thinking about, Francesca?
Yes.
Yeah. So those are not physical ghosts because they're actually, they only appear in closed loops in the standard model, and they are there basically to compensate for unphysical degrees of freedom, if you think about it. So they're not physical. So that's why these ghosts in the standard model, the Fadeev-Popov ghost that appears in path integral quantization, they're harmless. They're not physical, right? Now this ghost that appears in modified gravity, they're totally different. They're really real particles like tachyons and things like that that can destabilize the theory. So one must be very careful when modifying relativity.
So, Rogerio, there is another question. So the definition of delta C is Cg minus C.
Yes.
Does
Correct.
it imply that the speed of graviton is larger than the light?
Well, this is the exercise. I want to give it to you. So in principle, the speed of the gravitational wave, in principle, could be different from the speed of propagation of light. And in fact, this theory is here. You see all these theories. So gravitational wave speed is this gray area here. So there are many theories, Horndesky, Galileon, beyond Horndesky, where actually predict a different speed of propagation. Now, you can answer your question just looking at this graph, right? So which one came first? Gravitational waves or light or light? Well, you should see it, right? That gravitational waves arrive first because this is 0 here, and this is like 2 seconds afterwards. But what I want you to do, of course, this is few. This can be, of course, errors, etc. But what I want you to do is to take this this piece of information. It was less than 2 seconds difference because again, there's some uncertainty or when the light can escape from gamma ray bursts, for instance. Anyway, so there is a you know that it has to be less than 2 seconds, and the problem I gave to you guys is to estimate what does it say about the variation of the speed of gravitational waves with respect to the speed of light, proportional to the speed of light. You see that, okay, I don't give you the answer, you estimate that, okay?
Are there more questions? Something urgent? Okay, Rogerio, I don't see anything. I think you can go on.
Okay, now we have to talk about not only gravity, but also matter, the right-hand side of Einstein's equation, if you want. So we need to add matter to the action. And the way you do it is just have a Lagrangian for matter, and you have an action for the matter. That's all you do. And from that, you can write an Einstein-Hilbert action plus matter. Some examples that you probably saw from the lecture of Andrea is the electromagnetism action, or a real scalar field action, which is given by the integral of the Lagrangian of the scalar field. So all of these are examples of matter that you can add to the action. And then in order to, if you want to solve Einstein's equation, you want to find what is the energy momentum tensor associated with that type of matter. And the energy momentum tensor is defined as being related to the variation of the action with respect to variations of the metric. And this is the definition. The energy momentum tensor is related to the action in this way. And therefore, given an action for the matter, you can compute what is the energy momentum. And here are some exercises also that I left for you to do. One can show that for a real scalar field, meaning Lagrangian here of a real scalar field, the energy momentum tensor is given by this, d mu phi minus Lagrangian times g mu. And also, this is simpler to show, is that for a cosmological constant, the energy momentum tensor is just, so if you put the cosmological constant on the right-hand side, if you just write an action for the cosmological constant here, but this is just lambda, the cosmological constant, you find that the cosmological constant, you can write the energy momentum tensor as this, as lambda times g mu. So the energy momentum tensor of a cosmological constant is just proportional to the matter. And that has interesting consequences. So in order to solve this exercise, you can use this this identity here, because you have to compute the variations of the metric in this when you do this variations here. Anyways, this is a standard, and you can probably find this in different places, but you can do it just looking at the notes here. Yes.
Rogerio,
Yes.
There is a question.
Yes.
From Arpon. So, from a theoretical point of view, what are the requirements that are to be ensured for a credible modified gravity theory?
What word did he use? A credible? What was the word?
A credible modified gravity theory.
Credible. So you have to define credible for me. I don't know what you mean by credible. So there are good people that are working all these things. So do you think Lorentz symmetry is some sacred symmetry of nature. If you do that, you don't do this part of the modified gravity, right? So if you want to conserve Lorentz symmetry, for instance, and you want to still have massless graviton, you can only add, and that goes by the name of the simplest model, one of the early models of modified gravity with one scalar field was called Brzezinski theory of gravity. So I guess here, when you say credible, I don't know how to answer this question, because depends, depends what you think, what do you think credible is, right? So all these theories people are developing, all these theories have problems, and they try to cure those problems. So of course, if I have a theory that has ghosts and instabilities, and you cannot get rid of them by some clever choice of parameters in the theory, I would say they're not credible. Most people will say it's not credible.
Okay, yeah, he was, so Arpon was specifying, so let me read. I mean, we cannot just propose a theory, just adding more and more terms in the Lagrangian.
Well, one thing you can do, for instance, is this thing here. You can make an expansion in R, for instance, right? And this is, when we have lectures this afternoon about effective field theories. The effective field theories are expansions in derivatives of the field. So this is, you can think of this as being an effective field theory of gravity, right? It's just expanding in higher order derivatives of the metric. And this is something that people have done and in order to modify gravity. This is, this book that Andrea mentioned for standard model by a physicist called Donahue. He has also done lots of work on effective field theories for gravity, just as expansions in the Ricci scalar. Of course, you can go more complicated. You can also expand in the Riemann tensor square. So there are all sorts of theories you can do. So when you go beyond gravity, it's a can of worms, right? There are many different models, and it's difficult to say what I mean by credible. All I want to say is that at this point, there's no evidence whatsoever that one needs to go beyond general relativity and the cosmological constant.
Okay, so there are a few more questions, but do you want to answer them now, Rogerio, or do you prefer to finish and then we go?
Yeah, I think people should also hold questions for the Q&A session.
Okay, so guys, we come back later on to these questions.
Yeah, please take note, because I like to be provocative, so some of the slides are kind of provocative. So it's nice to have discussions like that.
Okay. Cool.
Okay. So we are here, and so I hope you understand that there's a well-defined procedure to computing a energy momentum tensor given a action Lagrangian for matter. Okay. Or something. So finally, Einstein's equation for GR, they're obtained just by requiring that the total action is stationary under some variations. Okay, this is how you get Einstein's equation. Now, I want to stop here for a few minutes because I want to do a historical interlude. I want to allow myself, because something important happened last year, actually. So last year was the 100 years of the confirmation of general relativity. So I want to explain a little bit how this came about in 1919. So the first test of general relativity was in the solar eclipse that happened in May 29, 1919. And so the idea is very simple, right? The idea is actually Einstein already proposed this, and some astronomers were looking for this effect. So if you have a star here, and it's close, it's the direction of the star is close to the sun, so that the light from the star, when it reaches us, passes close to the sun. The gravitational field of the sun changes the direction of propagation, bends the light. right? And you actually see the light of the star. You think that the star, you see the position of the star changed with respect to the position of the star when the sun is not there. So this idea was actually also happens, this deviation also happens in Newtonian gravity. And in Einstein gravity, in general relativity, there was a factor of 2 of respect to the Newtonian prediction. So the British, they organized, the British Royal Society organized 2 expeditions to look for this effect during the eclipse of May 29, 1919. So one expedition went to an island of the west coast of Africa called Príncipe Island, and the other went to Brazil, to Sobral in the northeast of Brazil. One was headed by Eddington, and the other was headed by Crumlin. And this is just one picture of the what happened at that time. So if you look here in this map, this is the region of the solar eclipse. And that's why they chose this island here and Sobral here. And this is a depiction of the camping grounds in Sobral, where there were also other expeditions, not only the British, but there were many people, because people always go to see eclipses and take pictures to study different effects. And this is the effect people were looking at, the deviations of the actual position of the star due to the presence of the sun, which it was actually blocked by the moon, so you could see the star when the light of the star passed close to the sun. So the effect would be that you would see the star looking a little bit displaced from its position without the sun. Of course, these arrows here are greatly exaggerated. And of course, the farther away the star is from the sun, the smaller is the effect. Okay? But this is just to show what is the what would be the observed shift in the stars. So this is the equipment that was used in Sobral. So there are many pictures of the expedition to Sobral, and there are no pictures for some reason of the expedition to the Príncipe Island. And there was also a Brazilian team looking for other things, but they met with the British team. And this guy here that I'm pointing at was the then director of the National Observatory of Brazil, Henrique Morizi, which is one of the old, I think is the oldest institution, scientific institution in Brazil, National Observatory. And the astronomers from England are here also. Crumlin is here, for instance. Okay. And this is the conclusion of this 2 expeditions. So this is the paper that was published in England in November 1919. The determination of the reflection of light by the sun's gravitational field from observations made of a total eclipse. And this is just the summarizing conclusions, is that in summarizing the results of the 2 expeditions, the greatest weight must be attached to those obtained with a 4-inch lens at Sobral. So the data obtained by this telescope, this 4-inch telescope at Sobral, was the data which has the greatest weight. And I can't resist telling the story. First of all, the weather in the Príncipe Island was not very good. So the plates from Príncipe Island were very imprecise. And in Sobral, also in the beginning, it was a bit cloudy, but then it opened up and people could take pictures. And the funny thing is that the British, they brought 2 instruments to Sobral. One was to be a step instrument, was to be used only in case the main instrument did not work. The step instrument was this 4-inch lens. Main instrument was an 8-inch lens that for some reason it didn't work. I mean, I think the heat or something happened, it didn't work. So all the data was, the best data was this step telescope. And this is the conclusion of the paper, that the results of the expedition to Sobral and Príncipe can leave little doubt that the deflection of light takes place in the neighborhood of the sun, and that it is of the amount demanded by Einstein's generalized theory of relativity as attributable to the sun's gravitational field. So this was the first confirmation that the general theory of relativity of Einstein was the correct theory of gravity, and then 300 years of Newtonian theory were proved not to be completely correct. Einstein became immediately a very famous person, and this is something that Eddington read at the Academy in England. So after a careful study of the plates, I'm prepared to say that there can be no doubt that they confirm Einstein's prediction. A very definite result has been obtained that light is deflected in accordance with Einstein's law of gravitation. So this is, of course, it made headlines, and this November 9, and Einstein became the man of the century, not only because of that, it was when Einstein became famous almost overnight. And this is nice. When Einstein visited, so Einstein was not in Sobral, right? But he visited Brazil and Argentina in 1920, and Uruguay in 1925. And this is a picture of Einstein visiting the National Observatory, and this is the head of the National Observatory, the same person that was in that picture in 1919, Enrique Morizi. This is Einstein, of course. And when Einstein visited Brazil in 1925, he declared to local newspapers that the idea that my mind conceived was proven in the sunny sky of Brazil. That was a nice. So there were early attempts also in other eclipses. In particular, there was an eclipse in 1912 when people tried to measure this effect. It rained. Then they tried again, I think, in 1914, and then there was the Second World War, and the astronomers went to EMEA. They were captured as spies. There's a whole history of this, but the first eclipse that was observed and tested was in 1919. And so there was, of course, a celebration in Sobral. We have even a stamp issued by the post office, the Brazilian post office, celebrating the eclipse. And there's a statue of Einstein in using shorts and sandals, so very typical from the Northeast in Sobral. So it became an attraction. So sorry about this. I couldn't resist giving you this historical interlude, and this is the end of it. Okay, so now we're ready to tackle the issue of the dynamics of the universe on average. And this goes, first of all, with the observation that the average universe is spatially homogeneous and isotropic. And the way to describe a homogeneous and isotropic universe is with a metric which is called the Friedmann-Lemaitre-Robertson-Walker metric, or FLRW. And for a spatially flat universe, so this metric can be also written for non-spatially flat universe, so curved, even positive or negative curvature universe. But for simplicity, and also because now we know experimentally that the universe is spatially flat, I use only the spatially flat version of the FLRW metric. So it's very simple. It only depends on one function here. So this is the metric. So it's dt squared minus this function here, which only depends on time, doesn't depend on space, which we call the scale factor, actually, a of t squared times the distance squared. So you can write the metric in a matrix form like this. And so if we have the metric, we can do everything that we want. Well, actually, in this case, with this very simple metric, we can solve exactly this 10 nonlinear differential equations, which are Einstein's. And actually, you can do that as an exercise. So as I was saying before, the Friedmann-Lemaitre-Robertson-Walker metric is determined by just one time-dependent function, which we call the space factor, the scale factor, a of t, and distances in the universe, which is something we're going to discuss a lot during these lectures, all measured distances in the universe. distances in the universe are set by the scale factor. Not only distances, but the speed, the velocity of expansion of the universe is the time derivative of this scale factor. The acceleration is the double time derivative of the scale factor. So everything is given by the scale factor. The scale factor is the key function that we have to find out to study how the average universe evolves with time. And before continuing, I just want to make an observation that sometimes, I'm not going to do this in this lecture, but sometimes it's convenient not to work with the time, t, the usual time, something we call the conformal time, which is related to the usual time by this expression here. So d eta, the conformal time, is dt over a of t. So that in this, using conformal time, you can write the metric as this. So it's just a factor of a square of t and the Minkowski metric here. And so in this conformal time, light rays goes in 45 degree lines. Useful sometimes. So by convention, we adopt that the scale factor is 1 today. So it only gets smaller in the past because the universe is expanding. So if you roll the movie back, scale factor is smaller in the past. And physical distances can be related to distances that do not change in this average universe. We call it a moving distance. So this zero here is an example of a distance that does not change, because if you take out the expansion of the average universes, take out the expansion of the average universe, then objects like galaxies, they don't move with respect to each other. All the motion in the average universe is due to the scale factor. So these are called comoving coordinates or comoving distances, which are related to physical distances by just multiplying by the scale factor a of t. So the average evolution of the universe, again, just to emphasize, is specified by only one function, scale factor a of t. And the scale factor determines measurements of large-scale distances, velocities, and accelerations. And we can measure these things through standard candles, like supernovas, or standard rulers, and I talk about this later, like K related to the cosmic microwave background, this baryon acoustic oscillation peak, which I mentioned before. Okay. And another quantity that we use a lot is the redshift. The redshift is just the fact that when galaxies or objects are moving away from us, if they emit light, this light, the spectral lines are distorted due to the Doppler effect. And you can measure the displacement, and this displacement is called the redshift. So the redshift is basically the ratio of the wavelength of the emitted light with respect to the wavelength of the observed light. And you can relate the scale factor to the redshift in this manner. So the scale factor a of t is just 1 over 1 plus redshift. And of course, if this is 1 today, if the scale factor is 1 today, redshift is 0 today. So there is no displacement of a line if the line is right in your laboratory, right? Exactly what you expect. So sometimes we refer to time in the universe as time t, or you can relate time t with the redshift. Sometimes it's more useful to talk about redshifts than cosmic time. These are interchangeable quantities. You can do either time or z, or sometimes even the scale factor as time. Okay, so the expansion of the universe, we parameterize the expansion of the universe as with the Hubble parameter. So the Hubble parameter, which is a function of time or redshift, is given by the time derivative of the scale factor divided by the scale factor. So that's the definition of the Hubble parameter. And so that's the expansion rate of the universe. And what we call the Hubble constant is the value of the Hubble parameter today. So when I put an index, subindex 0 here, I usually I'm referring to quantities today. And something, analogies are not perfect, but you can make an analogy of the expansion of the universe with a balloon. So if you have a balloon and you paint in balloon some dots, and let's suppose the universe, the whole universe is just the shell of the balloon, and you inflate the balloon, the dots will move away from each other. So it's like space expanding, like the rubber of the balloon is expanding, and the galaxies go far away. So that's one picture of the expansion of the universe. So one exercise that I wanted to do also, show that again, you have the metric, you can plug in and find the Ricci tensor, you can find the Ricci scalar. You can find the Christoffel symbols first, then the Ricci tensor, then the Ricci scalar. For this very simple, spatially flat Freeman-Lamont-Robertson-Walker metric, you can compute what the Ricci tensor and the Ricci scalar are. And this is an exercise I wanted to do. I really recommend you to do this. It will empower you. Is to show that the only non-zero components of the Ricci tensor are these. So R00, which is minus 3 a double dot over a, and RII, the spatial components, and diagonal spatial components, which is a double dot plus 2a squared. Actually, you can even guess that there wouldn't be any off-diagonal terms in the Ricci tensor. You know why? It's just because the metric is diagonal here. And the isotropy of the universe will not allow for any non-diagonal term in the metric or in the Ricci tensor. Okay, so you have the components of the Ricci tensor, then you can just compute the Ricci scalar. So if you have this, you can write the left hand side of Einstein's equation. Okay, so that's something I want you guys to try. And now, yeah, thank you. And now, again, I want to do a brief detour, because this is everything standard. And when I prepare lectures, I get bored with some people. So I want to do another interlude and make a quick tour to extra dimensions, okay? So bear with me for 10 minutes. So as I said, no, this has impact in theories of particle physics, the idea of extra dimensions. And I want to give a flavor of this, very, very superficial, but I want to give a flavor of this. I put here some reviews that you can look at for these extra dimensions. So the idea of extra dimensions, amazingly enough, goes back to Kaluza and Klein in the 1920s, not much after Einstein's general relativity work. But of course, they have been developed much further recently. So the first example I want to give you is a model called model with flat extra dimensions. So extra dimensions that have no geometry, just flat. This goes under the name of ADD. So ADD is not attention deficit disorder. It goes after the initials of the authors of this idea, Arkani Hamed, Nima Arkani Hamed. Probably you heard about Nima, Savas Dimopoulos, and Giat Valley. And this was 1998. It's amazing how old I am because I remember this when it started. So it was last century. And the idea is to have n extra flat space-like dimensions compactified in an n-dimensional torus. So the Einstein-Hilbert equation in this case will be an integral of 4 plus n, because there are n extra dimensions of the minus determinant of the metric of this 4 plus n dimensional space and the Ricci scalar for this 4 plus n dimensional space. And if you do dimensional analysis again, so this again is energy squared, this is dimensionless, and you see that this G star here, it has to have dimensions of e to the minus n plus 2. So if there's no extra dimensions, n equals 0, this is like e to the minus 2, which is what we have seen before. Now, this metric in this case, the metric in this case can be written as the usual four-dimensional metric and the extra metric from the space-like dimensions, which are flat. So that's why there's a delta AB here. So this is this very simple metric, okay? And this is just a figure I stole from a Scientific American paper by ADB 2000, trying to explain the idea of this extra dimension. So we exist in a wall here, or a brain, if you want to use some more fancy name. And so the standard model, everything that we know of the standard model is in this brain. So three-dimensional, one-dimensional brain. Only gravity can propagate in these extra dimensions. This is what this figure is meant to illustrate. And also this figure here is meant to illustrate. Now, in this case, one can show that this metric here, this metric, which is n 4 plus n dimensional metric, one can show that the determinant of this 4 plus n dimensional metric, since the extra dimensions are flat, the determinant is just the determinant of the 4-dimensional metric, and the Ricci scalar is just the Ricci scalar of 4 plus n space-time. It's just the Ricci scalar of the usual 4-dimensional space. So that the Einstein-Hilbert action, you know, since here, since here, this is just the usual 4-dimensional determinant, this is usual 4-dimensional. So you can factorize that into an integral d4x, dnx, and there's no dependence on dnx, so this will give you a volume effect. And this is the volume of this n extra dimensions. That could be a torus, for instance, as an example. And yeah, there's a question, but let me finish this and answer the question. So here you can see that the effective Newton's constant given by G star over Vn, that's the effective Newton constant in 4 dimensions. That's the usual, you know, Newton constant, and this has the right dimensions for the Newton constant, diluted by this extra volume effect. So this is an idea that was proposed, motivated to explain why the gravitational interaction is much weaker than the other ones, and the idea is simple: is that the gravitational interactions can actually propagate in extra dimensions, so the strength it decreases faster, and actually you have a decrease in the effective value of the coupling constant. So this was a beautiful result. And if you introduce a fundamental scale, like m star, given by 1 over g star, has dimensions of energy, you can write the Planck mass as being this scale here, n plus 2 times the volume. And you can also have fun with this model, just assuming that, suppose you want to estimate what is the size of this extra dimension. So you can compute the size of the extra dimensions, just assuming that the volume of the space is the dimension of one of the extra dimensions to the power of n. And then you can compute this, the size of this extra dimension n, assuming that the fundamental scale m star is 1 TeV, irrelevant at colliders, for instance. And then you can vary n. And what you find is that for n equals 1, you get 10 to the 11 meters. For n equals 2, 0.1 millimeters, and then smaller. So this model has excluded already 1, because we know that gravity works very well at this scale. Then if you go to large values of n number of extra dimensions, you have less and less constraints on this model. So questions?
So there are a couple of questions. 2 are on the chat, then there is the one by Allison. Let me read you the one in the chat. So what are the limitations of minimal gravity such that people look for modified ones?
Sorry, can you repeat? What are
the limitations of minimal gravity such
minimal gravity?
Minimal gravity, yes. Such that people look for modified gravity theories.
Yeah, so the motivation to look for modified gravity theories is the accelerated expansion of the universe. So if you think that the explanation of a cosmological constant is not satisfactory, some people look at modifications that could, in principle, explain the acceleration of the universe without cosmological constant, but with a much more complicated theory.
Then there is a second question, which is the following. So if redshift is 0 today, should it be negative in the future so that A, the scale parameter, increases? But light should be redshifted, not blue shifted, right? Does 0 = 0 means that we are reaching saturation in the cosmic expansion?
No, so, okay, no. The redshift, yeah, you're right. So the redshift would be smaller than 0 in the future. We don't see the future, right? So it doesn't make much sense to talk about redshift of distant of future objects. So we usually look in the past. We don't see the future. So yeah, so there's no light coming from the future. So you don't have to worry about seeing objects from the future.
And then there is this question by Alisson, who is raising his hand. So Alisson, do you want to speak?
Hi, can you hear me?
Yes.
All right, so I'm just curious about this idea of compactification on a torus. This is different from the usual Kaluza-Klein idea where you compactify in a circle, right? And you have the cylindricity condition and you can have the expansion, the Fourier expansion, and the modes are suppressed. Does the same hold for a torus, like the cylindricity condition?
Yeah, and you can do the same thing as in a torus.
All right, thanks.
But for this exercise, you can think of circles also, if you want. Anything else?
More questions for Rogerio? Before, okay, yes, there is one. Abhijit, please go on. Abhijit?
Yes. I want to ask.
Please, yeah, please go
My
ahead.
question is why the scale factor is function of time only? Is it because of we define the FRW metric in terms of the moving coordinates?
Sorry, I didn't understand the first part of the question. Can you repeat?
Yeah. So I'm asking why scale factor of the universe is function of time only.
Ah, yes. It's function of time only because we're talking about the average universe and things are homogeneous and isotropic. So it shouldn't depend on the position of the universe. So everything depends only on time.
Fine.
This is what happens when you are in a homogeneous and isotropic universe, which is the case for what we call the average universe.
Oh, thank you.
Okay.
So there is a curiosity, Rogerio.
Yes.
Is cylindrically symmetric space-time of any physical interest?
Well, yeah. Some time ago, people were discussing, okay, this is a digression. But some time ago, people were considering the effect of a non-trivial topology in the universe. Well, cylinders have a trivial topology, more of a torus. No, for cylindrical spacetimes, yeah, it's just easy to study compactification cylinders. I was thinking about torus. For torus, people have thought about the non-simply connected geometries. Some time ago. Then I can tell you why I don't believe in this later.
So more questions? Okay, so I think this is a good moment to stop also because then you guys can think about the lectures. So just to remind you, at 2 p.m. in Brazil, we will reconvene for the question and answer session. So please bring your questions. The speakers will be there, Mr. Rogerio and Andrea. And after that, we will have the third session of lectures of the day with Riccardo Pencu about effective field theories. So Rogerio, thank you very much for the very nice lecture. And we reconvene in a while. Thank you everybody for the attendance.